Hi everyone. We can just wait for a few minutes and then start. In the meantime, if you guys have any questions, you can ask me. Yeah, sure. Okay. So the colon thing actually usually comes in the context of namespace. Okay. Uh, Usually that. But the second thing is also when we have classes. Right. So we've seen the examples, but I'll just uh, bring that up again. Let me search for the share my screen and then show you guys. This would be at this thing. So okay, cost plus that's one. All right. Um, let's look at. Yeah, sure. Differences. Yeah, certainly no problem. Let's look at the usage again. I think that will clear the doubts. So should have it so much here. The static. Yes. Okay. All right. Yes. Got it. So let's keep this as one example. And we saw, I think, vectors before, so I'll check that. Actually, we can't itself. Let's go with that. Okay. So yeah, here also. Right. Okay, let's take a simple example. Ignore the custom namespace, whatever line, but okay, this I don't know why this happened, but okay, ignore this too. So, oh, sorry, that's my bad. That's absolutely okay. So yeah, so let's look at this code. So we have an integer a equals to 2 and then left shifted with 2. Okay. So this is like multiplying 2. As in, if it's shifting left, then I forget, but I think this is multiplying by 2. So 2 times. So this is a shift operator. But anyway, end of the day, the point is a is some integer and we want to print it. Okay. So if you see this function, so cout actually is a function. This is a usage where the shift operations are overloaded. Okay. But the point here is standard cout expects some input. Just so happens that you can have strings and a number, okay, integers, doubles, or something like that, as in whatever this supports. So inbuilt data types like strings, as in characters, integers, double, and all. Sorry, excuse me. Yeah. So these are expected as the input for standard cout. Okay, cout is the function. It is defined under some namespace called standard. That's when we use double colon. Okay. So double colon is used in two situations. First is the namespace that we are looking at here, which is a standard namespace. Similarly, yeah, you can use dot, yes, but you have to remember cout is a function, it's not a member. You use dot for members. So member variables, right? Those are, for them, you use the dot. Okay. You use colon for functions. Okay. That's how the distinction has been done. So if I see the custom namespace, like something like this, uh, yeah. So inside the custom namespace, I'm calling that as a namespace. I define two functions. We have cout and an add. Cout doesn't take anything. Add does take some things. in class, we use dot for internal function too. For internal functions, you don't need to actually use any dot. I mean, if they're accessible, I mean, any function inside a class is accessible to the class. So can give an example where you use the dot for internal function too. I mean, it's technically speaking, probably you can, but dot is usually used for as in okay. I see what you're saying. Got it. Um, how do I put it? Mm, Yeah, this will clear the things. Okay, I see what you're saying. So there is a namespace, okay, which is a custom namespace. Fine. It has something called a function. It has something called an add, which is also a function. This is a void data type. This is integer. Just it can so happen that inside the namespace, I can define something called a class. Okay. My bad. I think I misunderstood what you're asking and maybe said some wrong things. But okay, I'll clear things up. I think this is a better way to go about it. So I have a custom namespace. Inside that, I have some function. If I'm accessing some function, add, which is inside some custom namespace, I have to use the colon to refer to that function. Okay. What I'm saying is a namespace is just that. It's a name given to a bunch of a collection of functions, collection of maybe members, or collection of classes even. You can define a class under some namespace too. In that case, to access this class even, right? So let's say you define a class called circle. To define that in classes, so for example here, like a class called complex, you have to define the complex and then define your object, right? As in, this is the syntax for it. To even write this complex, right? In, let's say for circle, you have to give custom namespace ::circle. Okay. And then further define C1 or C2 or C3. Let's say this complex class is inside a namespace called custom namespace. Okay. Then you have to use the ::. We don't always write it in a namespace. No. We do use standard namespace. So actually, I'm have been using standard everywhere. You can use using namespace standard. That is a valid code, but it's again, like I said before, it's not recommended to use namespace something and then start calling functions because sometimes it gets confusing where the function actually belongs to. So for example, here custom namespace to access the function add, it's not inside this other namespace like the main namespace. So I have to use custom namespace : at and pass values. Now here's another important thing. Inside the namespace, okay, there is a function called cout. There is a cout defined under standard. To avoid the name collision, you have I can't just use cout. I have to use it with standard cout or custom namespace : cout. Yes, this is a function defined. I mean, you can think of it even like uh, a special looking function. It doesn't have any brackets. But the thing is, the main point is this is defined under standard. I mean, technically, it's also probably a class itself. You can hover and see. We don't. But yeah, here it won't be. We won't be able to see it. Okay. Here also a custom namespace. Got it. Anyway, so the point is when you're accessing something from a namespace, you have to use : Okay. But there is another thing also, like here. To access the my class, okay. So the data type of my, so okay. The custom data type is data. So you access it here. That's fine. But to access a data member of my class, you have to use : So these are the two cases you have to use the : as in to access a data member, okay, of a class, right? Here Yon should be careful. It's not a defined object where you're accessing the member. You're accessing the member from a class. Okay. So because it is static, right? Static has its own syntax to access things. This is a special case, yes, but to access them, right? Each member, because they're static, they will be shared by all the objects. Okay. So my class, you have to write and then access, then by D1, D2, D3 through colons. So this is the main two things where you'll see colon being used. One is the namespace like standard or your own namespace like custom namespace, let's say. And the second one is where you access the actual data members, but for let's say so for static. It's not for everyone, yes, but for static, yes. For static, you have to do. Question. We always write our code in namespace. Why don't we use for calling our custom name class? Yeah, so actually what happens is because your, let's say, whatever you're calling is already inside the namespace. So then it doesn't need to know the full name. So it works. But actually the good practice will be to always give the full namespace with the code with the full namespace and everything. Basically, if I have to call a class or function from a defined namespace, that's all. Then only we will use colon. That's all. Yeah, pretty much. If you have to want to call a class or a function from a defined namespace, correct. But I usually recommend to do that because it actually clearly signifies where the thing is coming from. Because it makes a code lengthy, yes, but readability takes priority and maintainability too. So yeah, awesome. Any other questions? Oh yeah, you had more questions. So dot and others too, right? So colon, I guess makes sense, right? So mm, let's take example of this. If I want to access members, but from the object of the class, then we use dot. Oh, okay, sure. Should I explain the arrows too, the arrow operation? I can. I mean, it's okay. I'll go ahead anyway. Okay, awesome. Awesome. Yeah. All right. So, right. Okay, we can maybe recap what we saw last week. This is done. Okay, class is also done. Yeah. All right. Last week we saw about cost casting, right? So let's say there is a integer defined I equals to 10, which says I have a variable which I'm storing I, which I call I. I'm storing 10 in it. It's an integer. Okay. This is pretty much standard. We all have seen it. The next step, what we do is we define as something called a pointer, PTR, an integer pointer, mind you. And when I say equal to, what will happen is I'm storing a address to this pointer. Always remember, pointers always store addresses. The data type they are qualified with, and whatever the asterisk is, it says that it's the pointer, yes, but the data type it qualifies before, okay? It says what is the data type I am pointing to, as in what is the data type that is whatever address I'm storing, it contains some data. I will treat that data with some bytes, as in some units to access them. And what kind of data will that be? That's what the pointer says, okay? But in itself, the pointer will always store addresses. In this example, I'll give it the address. Okay, so here the ampersand, again, remember the ampersand depends on the context as an address or a reference. Here in this context, it means an address. And with this ampersand I, what we want to say is I'm taking the address of I and storing it in PTR. Okay. In this example, next example, I write it as integer ampersand ref equals to I. Again, in this context, ampersand means reference, not address. So integer reference, okay, I'll call that reference as ref and make it equal to I. What it means here is for all intents and purposes for this code or in this scope, I and ref are exactly the same. They share the same address. The code will probably treat them as the same. Everything is same. Okay. So if I change ref, I will change I also. Technically speaking, even pointer, PTR pointer, okay, will change I too because it has the address of I. Okay. Now let's say one changes ref to 9, then we print it, we'll see the change reflected, 10 changes to 9. Okay. Now in this, coming to this example, okay, where we keep the integer I as 10, fine. But this time, these pointers and reference, we change them to const. We const qualify them. As in, now it's a pointer which is const qualified. It's a reference which is const qualified. What does it mean? It means that this pointer cannot be changed. As in, it cannot change the data it is pointing to. This reference is a const reference. It cannot change the data it is pointing to or it's referring to. Essentially, that's the idea of having const. But mind you, the difference is that here the integer, the originally defined variable where it actually stores the data, is still not const quantified. As in, it is still editable. You can change the value at I. But through pointer PTR and ref, you cannot change the values. That's the motivation behind const qualification. So when you write code, okay, you might pass variables or values or pointers to something. But inside the function, so let's say we write, I guess the vector example is also good enough to see this. No, not here. 2D array, no. Should have the heap vector or something like that. Sorry, just give me a second. I'm looking for that example we saw before. Sort of, yes. Yeah. That's sort of the idea. Yeah. That's how you get to encapsulation and abstraction. The basic building blocks are more or less known to you guys now. There is namespace, there is functions, member functions, classes. And classes have their own defined properties. Like you can make friends, you can make private, public members. You can derive classes, right, from parent and so on. Yes, exactly. It's internally the same process. So these, whatever I just spoke of, these are the building blocks. Okay. And from this, you build everything else. So all the ideas that are come, like you take a bunch of these, let's say there are 10 ideas. You take a bunch of them, like 3 or 4, and that becomes a new idea. That's one of them. It's like, yeah, abstraction and encapsulation are basically built on all this. Yeah. The main basic fundamental things are all whatever we have discussed till now. Yeah. So there should be one. Yeah, sorry, my bad. Here it is. So you see this function, right? There's a function, and I'm calling this, right? So here it is overloaded. There's same function, but here it takes some different inputs, and here it takes some different inputs. So I guess you guys should be able to distinguish between function overloading now. So essentially, the idea is that you have still the same data type return, right? And same function name. Just so happens that the parameters it takes are just different. So that's function overloading. In this case, the B it takes as a reference is not const qualified, but assume that it was. The motive behind functions like this is when you pass by reference or something, B cannot be changed. Or if it was a pointer, it cannot be changed. There are cases you want to have this, not for this example, but imagine cases where you pass by reference or pass by pointer, you const qualify it here, but the actual variable could just not be const qualified. So for example, like we saw here, it could be integer I, but while passing to the function, PTR could be inside some function. Like let's say, maybe I can just write here and give the example. Could be const int ampersand ref. And while calling the function, I'll just call it as I. Okay. So here let's say I have some body to do the code. Okay, whatever. Right. So the idea is that I itself is defined to be not const, but while passing to ref inside the function, okay, it will be uh, constant. You can't change it. Now, that's where const cast comes in, okay, to temporarily change the constness of the variable of the reference or the pointer, okay, so that you can change the data. That's where const cast comes in, okay. Important thing, const cast can only change the variable or value only if the originally the variable which is defined is not const, as in it can be changed. Okay, we took the examples and saw the outputs. You can run this and check errors, whichever will show, and so on. I mean, here, yeah, again, you can uncomment and see this outputs. The point is, there are two ways of doing it. One is the C way, which is casting the reference, which you define here, and temporarily typecasting it to be an integer reference, not without the const. So you can change it. The C++ way will be having the const cast, passing the template as what you want to actually change it to, and passing the variable to the as the input. Okay. Here it was dereferencing the pointer and changing it to 9. Again, gives an error because it is const qualified. The C way is to cast it as integer pointer, okay, and put 9 to it. But so happens that it's with integer pointer, you can't just cast it and change it. But there is a way, at least C++ allows you to do this. So const cast it as integer pointer, dereference it, okay, pass the pointer, and then substitute 9 to it, as in set it to 9. Yeah, it is quite amazing, yes. So C++ has been um, quite at least I feel it's quite thoughtfully created. As in at least a lot of these newer standards after C++11 have all these modern features, have a lot of thought put into it, and hence sort of the idea behind the course to learn all these modern features. As we'll see later, like in coming next today and some few weeks, uh, some of the features I'll discuss are quite amazing, as in they make writing codes and maintaining through like a, a real breeze. Also, you do not lose on performance even. So it's actually quite amazing. Yeah. The main idea behind C++ was actually performance. I mean, that's one of the main reasons it's still alive. But people do want maintainability. So, and a lot of people are used to writing object-oriented programming like codes. So C++ gives you both. You can do functional programming or you can do object-oriented. We will look at functional programming also. And object-oriented is what we have been looking at, like classes, objects, and such, and so on, right? So C++ does give you both options. It's up to you to choose. People tend to use object-oriented a lot, as far as I understand, but you can feel free to use both. Yeah. All right. It's not about need, it's about preference. I mean, honestly, I'm not the expert to comment on this even. I myself have been mostly used to object-oriented programming because uh, the code that I got to work with was already written as in object-oriented programming, as in it was already structured. So when you try to extend any code, you can't just rewrite everything. So you take a existing huge 10,000 line of code or something and extend that. So you have to sort of build on that framework. So what, as far as I have seen, object oriented is more popular, as in whatever most of the code I've seen. So just people tend to write, oops. Yeah. Functional programming, I wouldn't say it is not necessary. Sometimes we do write it, uh, as in we sort of write functional programming kind of code because it's we don't need to write a function, right? I will talk about lambda expressions. So there are sort of like function programming. There, because we want to define some kind of function, but like a throw away function. So we just sometimes write those also. So yeah. All right. Recapping. Oh, yeah, lambda is actually quite useful also. And to be honest, if you are writing codes in SYCL, SYCL, which is the programming language by uh, it's developed, it's open source now, but mostly developed by Intel. That language can be used to program in all architectures, even Intel GPUs. So for performance perspective, ideally, we still, at least in our work, we still stick to writing CUDA programs for CUDA for NVIDIA GPUs, HIP programs for AMD GPUs, and SYCL programs for Intel GPUs, so that we get best performance for each architecture. We have wrapper functions for that. But the main thing is that when you write SYCL kernels or SYCL functions for Intel GPUs, or actually when you're targeting anything anyway, you sort of have to write your kernels in lambda expressions. So you're sort of bound to come across lambda expressions if you're writing in SYCL kernel. So yeah, lambda expressions are pretty much important if you want to write in. That's what I'm saying. If you're writing in SYCL kernels. So, yeah. Well, the syntax is different for kernels in CUDA and HIP. HIP and CUDA are pretty much the same. But yeah, for SYCL, you kind of have to know function programming in a way because you're using lambda expressions. Right. So this, uh, as far as I understand, they should be similar. I'm not familiar with how C Sharp or Java does, but I expect probably this idea would be the same. So yeah, yeah, like this was the dot function you're asking me. So that's fine. Well, we saw constcast and some references. That's fine. Now moving on to typecasting. Right. So again, we'll define variables. Yeah, sorry, this is weak. My bad, sorry. Yeah, anyway, we saw these examples, right? So integers, floats, and doubles. Implicit casting, explicit casting, and one has to be careful while doing a promotion or demotion, right? So if you cast a double to an integer, it can't store the whole data because it has to trim off bits, right? So you lose precision. So that's a trade-off. If you promote an integer to a double, you can probably exactly represent it because it's the same, it's just higher number of bits, right? So there you have it. Those are the examples. Then what we saw is the examples through pointers, as in can you set them or not? Can you cast them again? So we went into some details here. So essentially, the idea is that when casting pointers, one has to be careful because you are treating the data as new units. So if you are treating it as integer, which was 4 bytes, now you start treating it as doubles, okay, which is 8 bytes. You might run into set faults. That's one issue. The second issue is you're not treating them as how they were intended, maybe at first stored. So if 4 bytes was used to store data, like under some numbers, right? So if it was 1, 2, 3, 4, and so on, each of these numbers took 4 bytes, but now you treat them as 8 bytes. So the representation for 1 and representation for 2 combined will be the new 64-bit number, which you'll start reading. It might be some garbage or something which maybe you require it, but one has to just be careful. Okay. Right. So that's some examples we saw. Void function with void pointers also. One has to be careful because you can store anything to a void pointer, but casting as in casting anything to void is fine. But recasting, you have to be explicit. Okay. Like void pointed back to anything else. It won't be implicit. That's the thing. Next is some references, but through classes. Again, typecasting, right? But through classes. Uh, we define some objects of different data types. So A and B are the class names here. So you can think of classes as again custom data types. Setting them again, you cannot set this or even typecast them. So all this will throw error. So what we saw last time. Even pointer wise also, right? But you can set them as a different pointer because pointer casting is sort of allowed. You can think that way. When you try to access them, it will throw all sorts of errors. That's a different story, but still, you can do this. The next example I think we saw is with derived classes. Yes. So that was with classes which are not at all related. But if you have derived classes, in some cases you will be able to store them and some others you won't. Okay. That's what we saw last time. And yeah, next time is this one. So again, it's all about public and private data members so that you can access some data and cannot access some data and so on. Okay. Right. That's more or less what we saw last time. So this week, let's continue the const discussion. Okay. All right. Let's take more examples. All right. As usual, we'll include, oh, my bad. As usual, we'll include the stream header so that we can print stuff and see. This time, I'm actually going to write a function which I'll call as print. Okay. All right. So this print function will take characters called char. Okay. Question. Oh yeah, of course. Actually, it should be shared with you. I mean, so NPTEL has a Google Drive link. Okay. So there I upload all the codes of every week after every class also. So it should be accessible to you. If you guys don't have it, please mail to NPTEL. So they should, I don't know how they share it, but you guys should be having access to the YouTube links where I upload these sessions and also the link to the Google Drive where I upload all the uh, codes. Okay. So that you can just take the code and try it for yourselves. So this stdc out will just take the string and oh, I'll not call it card, sorry. Just call it string, str. And just put str. That's it. Okay. Let's define the main function. Okay. We'll define a const character, okay, something like C, which will store something. Let's go to the origin. Hello world. Okay. And line. Then let's say I call print P. Okay. What do you guys think will happen? And just return 0. Why not? Because always. Okay, any guesses? Will print C? Okay, let's see. Thrown error. So the reason for that is it doesn't have a matching function. One has to be a little careful to see that if your character, whatever variable you're passing is const qualified, if the function doesn't actually exactly take the same, it throws an error. Okay, I know it's a little, it was a little sneaky and tricky of me, but anyway, the point here is that it has to be const for it to work. Okay, so let's say I do this. Okay, it prints and that's all good. The percentage you see is because the what do you call it? The starting line to ZSH, okay, is percentage in math. So for that. Uh, anyway, the point here is that when you pass the variable C, okay, if it was not const qualified, then what do you guys think will happen? Again, the error. It's a warning mostly. It cannot convert something which is not const qualified. Okay. Sorry. So it was const qualified, cannot something which is const qualified to a not const qualified. As in year string can be changed, but you're passing something which cannot be changed. So hence the problem. But if you have something which cannot be changed, but and pass it to something which says cannot be changed, which sorry, when you're passing something which can be changed to something which cannot be changed, that is perfectly fine, because here in this context of or in this scope of print, string will not change it. And if you have a code which changes str, then it is how to put it? It will throw error, yes. But excuse me. Yeah. So in this case, we don't change it. And so hence const uh, sees that we're just printing it. So this is a perfectly valid code for it. Okay. That's the basic idea behind this. Fine. So this code is perfectly fine, as in you don't have a const, but here you have const and not change it. If you try to change it, it will throw error. Okay. So let's say this was the original code. Okay. And this is the what we have. Now to resolve, I mean, let's repeat so this will throw an error. To resolve this error, there are a few ways. What we see is we have to make a const here. But the problem is sometimes we have functions which, let's say there are a lot of functions which do not have const qualification, and there's some character or something. Then you have to make a const input taking function for each of them, which can be a little hassle, but yes, one can do this. So one can actually make a new function overloaded, right? So which takes const, and this resolves this issue. So it will work for both character const C case and without also, because correspondingly the print will be chosen. Okay. So it prints it generates an error. That's okay. Doesn't matter. Point is it will work. Okay. This is one way of resolving this issue. Okay. There's another way. Exactly. Maybe you can guess from the title of the code, name of the code. So what one can do is do the same print. Okay. But this time, instead of just passing C, I will, let's do the C++ way first. Const cast, it's the parameter pointer, right? So that will be character pointer. Takes the what do you call it? The parameter C, okay, and prints it. It's expects a pointer. I'm just going to cast it and pass the pointer. There's no dereferencing required because we're not accessing the data here. We're just passing the pointer. Okay. Now let's see this one. Yeah, it's the same exactly. Okay. We mentioned it. So this is the C++ style of just call it const casting. Okay. We can do a pretty similar thing in C style also. So that will be character pointer and just pass it. So essentially what's happening is the parameter that is going into print is between this parenthesis, okay, and this parenthesis. So the whole thing is sort of, we can think like it's temporarily being cast and then sent to the as an input to the function. Okay, same here. We're not changing the pointer, how it's defined, everything. It's just that temporarily we are changing it and passing. Oh, my bad, I should make it small. Okay. Yeah, that's fine. So yeah, sometimes you might get confused, but the idea is that const cast removes constness. It doesn't make it const, it removes constness. So the C variable first time, it was const. We cast it as character pointer, basically temporarily removing the constness and then passing it. Okay. For functions like this, you can temporarily remove it and pass it. That's basically the idea. Depends for both cases. Let's keep the C style first. Okay, works. Then the C plus plus, sorry, the first the C plus plus style, then the C style. Okay, works. I'll mention it. This is the C style of const casting. Again, you don't explicitly use a const cast function, but yeah, you just do an explicit casting. All right, I hope this is clear. Next example. Let's call it const casting. Now it's APP. Include IO string. Right. Let's take an example now with some classes. Let's define class A. Okay. Excuse me. So integer I, let's go some let's write this one. I is an internal member. We define public. Okay. So text, this is basically the constructor now. Text I underscore defines I to be I underscore. Okay. I think there is no body for the constructor required. Then let's write a getter function, get, and make it constant. So yeah, then I return. And I'm sorry, I. Okay. Then set function, which just takes values and sets. So there's no data type required for it. Takes integer. The text integer I, let's say j, and sets I equals to j. And we'll end it. Okay. Let's write the print function. Takes character pointers, yeah, basically essentially the same example we saw. Okay. Standard cout, xstr, and yeah, sure, why not a new line. Oh, and let's write the main function. Turn by 0. Okay. And we'll start with the same const character pointer str, or why not the hello world. Okay. So same example, pretty much, but this time we have a class extra. Same print function, same main function, same defined C. Okay. Right. So we saw this before. Print will throw error. So maybe I should mention it here. That's fine. Last week. This is I mentioned as error. And this is the case one. Next, let's say do print C. We know that this will throw error. Yeah. Right now we don't have the overloaded function, so let's just keep it this way. So we do print const taking the pointer character pointer, and that's the template, and pass v to it, pass it the function, and pass print. That's now let's define constant custom data type A. A is object called A. Because I have defined a constructor, it will expect an input integer. It will set that integer to its private member. Okay. I hope you guys are clear why it is private. By default, if nothing is mentioned, the functions or members become private. Okay. We make public here later. So these things are be public. All right. So I'll set it to, let's say, 2. Next, what we can do is this sets the whole thing. That's fine. Now we'll write a getter function. We'll call the getter function now. So this says the value of I in A is the A dot get. That's it. Getter function doesn't take any input. It returns the I, right? That's it. So this is fine. Okay. Now let's run the code. Okay. Yeah, that is the problem. So set function. Did I not take? Oh, my bad, my bad. Sorry for that. Yeah, right. There's a syntax error. Yeah, so a simple code where we're mostly writing the same thing. So if you try to print it using const cast, because character pointer is the only one which print function exists. So it prints the hello world. The second one, we define a, small a, as an object of class capital A, and call the getter function to get the value stored in I, which is 2. All good so far. Next, what we try to do is use the set function, as in the setter function. We'll set it to be 4. Okay. Then what has happened? This was an error. Reason is what we have defined A as in the small a, okay, to be is a const object, as in, um, okay. I think I'm audible. There was a drop. Okay. I think I'm back. Yeah. So, right. What I was saying is the object A is, yes, right. This is how you have to be careful with qualification, as in the whatever the qualifier that happens to your objects or variables. Okay. So this is the custom data type, but there is another qualifier, which is the const. Because your object is constant, you cannot change the internal variable. So this argument to member set has type constant. Okay, but function is not marked const. So that's what you have to see. The getter function, I wrote it as const. Here the set function is not const. Also, that is there. If it's not const, you could have said you setter. Yes, exactly. That's what we've done before in some examples, where we use setter function to set internal variables. I think this was a question asked by someone also before. What's the getter and setter function? Essentially, these are the ones. But because your object is const qualified, you can't just use set to change it. Okay. All right. But can we do something else? Okay. Let's see. We can. So this one for error. Okay. We will const qualify again. As in, sorry, cost cast it, right? As usual, if we can we get away with it. So we will make a reference, okay, for the same A, right? So now we'll pass that A. Sort of like saying that we will treat it temporarily without the const. Yes, okay. And then do a dot, call the set function, and let's say path 4. Wait. Okay. Let's now see if we can change it. change the internal variable and see. So this will print a, right? Dot get should print I again, and set function, if it is able to set I, then we should be able to see it. Okay, let's see. All right, great, works. So that's the idea. An object defined to be const, okay, can be temporarily treated as a not const and used to set or change some member variables. That's essentially the idea, because the original variable is not const qualified, as in the integer I can is able to change. Okay. Now here the reference makes sure that you are treating the same object A, okay, and changing it, right? What if one does this? Same thing, but instead of reference, I'll just cast it as A, okay, and then use the set function. What do you guys think will happen? Check it out. This throws an error. Yeah. The reason for that is we can't just change the original variable. Okay, the original variable is actually const qualified as A. We can't change it, but we can sort of treat a new, you can think of it like a new pointer or new reference with respect to that, and then work with it. That's what we saw in the starting, oh, sorry, my bad. Starting case also. Integer I itself was not const, but the references or pointers created to it were const. Okay. So this pointer and reference, we can't change them to be not const. They are already defined to be const. Okay, we can't cast them to be whatever. But for temporarily treating the data, right, changing some values referring to it, which is I, you can temporarily change it. You can't change reference itself. Okay. But what you're doing is you are treating it a little differently than it is right now. That's all. You're not actually changing it. So that's what happens. So you can't change the object A. What you're doing here is already const qualified. You can't change it. But temporarily, I can take a reference, okay, which is not const qualified, and change this internal variable, which is I. Okay. So this is an error. Right. Let's see. You can actually do that. You can take a pointer, then you have to be a little careful. This is just easier to write, so I just wrote it this way. But you have to be careful there because you're passing pointers, and then you will have a star, right? So to access the function, is that okay. So yeah, so what I'm saying is, yeah, because you're having a star as an a pointer, then you have to be careful to use the arrow operation, because accessing a data member of some pointer gets a little tricky. You have to dereference the thing and then do all that. So I'll leave it as an exercise. You can do it, yes. Okay, next, all right, next example. What is spelling correct? I think so. Okay. So again, hash include IOStream. Make a class A. Actually, maybe classes won't be required. Yeah, that's not required. The main, the what do you call it? The original function, which always has to be there. You have the return type. Okay. Let's make a long number. Okay, only 8. Okay, a double D, and let's say this is for 9. A double pointer. Okay, or pointer to D, and store the address of D. Perfectly valid. D is already double, and we define PTRD, a pointer D, okay, variable, which is a pointer. So, and of data type pointer, double, right? So, storing address of D is perfectly valid, right? What if one writes L equals to PTRD? What do you guys think? Like, this time this will be, yeah, was an error. So again, I need not even say why the error is. It's already pointed out to you. So it's an incompatible pointer to convert integer conversion from long to a pointer double. Okay. So long is a um, number, as in it stores numbers. Pointer D actually has an address. Okay, it stores an address. Technically speaking, you should be able to store an address to long because it's an integer. And let's think of it like long is here, what do you call it? Um, 8 byte, as in, yeah, this hierarchy, yes. But long can store 8 bytes. Double is 8 bytes. Long can also store, sorry, my bad. What I'm trying to get at is pointer D itself stores an address, which is of 8 bytes. L is of type long, so it can actually store 8 bytes, but directly storing or like casting something like this, it's implicitly not allowed. That's the main takeaway here. Throws an error because implicitly it's not allowed. So one way is let's see the C style way. Okay. Cast it to long, PTRD, and then store it to L. Okay. This I've given the answer, it should actually work. So yeah, it actually works. So you cast the pointer to be long now, as in not the double pointer or something, but temporarily just long, as in the pointer D, which stores an address, which is an integer. Okay. It's casted to be as long and then stored in L. Okay. You can actually try to press L and see what it actually has. So L, let's put it here so that we know the two outputs that it has before and after. First one, oh, my bad. Sorry about that. The first one, it stores 8, which is what we're storing. That's fine. The second one is long, which it shows you some number, right? Now this number is essentially an address. Just so happens that we can't make any sense of it, but that's the thing. It's an address stored in pointer D. Okay, now that's there in L. We explicitly casted it through the C style way. C style casting. Okay. Actually say explicit casting. That's better. All right. Now let's look at the C++ way of doing the same. But since you are actually converting a data type to another, we use something called a reinterpret cast. Okay. This is something which is defined in C++. So if you think about it, there is casting here. Okay. So we have seen type casting before, right? These are the type casting we saw with explicit or implicit, right? All of this. So essentially the same thing if you want to do, right, from one type to another. The C++ way is actually this. So you use the interpret cast, right? Here, yeah, pretty much everywhere we use the CUA. It is all C style ways. And yeah, it does make sense to learn the C++ way also. So here it is. You passed it into long, you pass the data type into the template. We will cover templates, but that's essentially can take for now. Within the single angular brackets, this is the template. You must have seen it in standard vector definitions. Suppose you define standard vector, then give a template to the as a data type, and then define the vector. Then the parameter, which is the pointer. So it reinterprets that and stores it in L. Yes, it is true that there's only one syntax. So excuse me. There's only one syntax for C style, no doubt. But thing is, there is a reason why we have different ways of doing the same casting. As in, we have const cast explicitly. There, you do not have to do const casting. Just use a plain old casting. C has only one way. But to do the same, we have const cast separately. But again, it depends on the context. Here it's reinterpret cast. The reason for that is it makes the intent clear. When you are casting something like this, you are converting something to whatever this is. But the intention is not exactly clear always. Are you removing the constness? Are you just changing the data type? What are you doing? So hence the reinterpret cast and const cast so on exist to make your intention actually clear. As in explicitly say, what is what is it that we want to do in this code? Okay. And let's say we read it. Okay. Well, I'll comment this for now. Okay. Okay. Let's print it first and then same output works. So it's the 3 plus plus and preset casting. All right. I hope so far so clear. Internally, what happened? Internally, it's written such that it follows the rules. But yeah, visually there is not much change. As in, this is C doesn't distinguish between the intention or something, but C++ has different functions for the intention. That's all. Essentially, performance-wise, you should not notice any much difference between these two. But that's the nice thing about C++. You do not lose much in terms of performance, pretty much, I would say. But what you gain is better code readability. Sorry, my bad. So yeah, in terms of better code readability is what you gain. And the performance are always there. Yeah. So if we're having a pure C++ compiler, then we need to use this. Yes, that's true. That's correct. Usually, when you have C functions or C things, it can get compiled by some compilers. But if you have C++ purely, then yeah, you have to stick to this. Ideally, yes, it's better to stick to one programming language in your whole code. So yeah, that's better. To check this, actually, and not only take my word for it. So let's say the the size of it. Okay, it is. You can use the size of function. Okay, size of long. Then the ENDN. Okay, print state. That's essentially what I was getting at. The shows you the bytes of that internal data type, as in what is happening in this. system architecture after the compilation and running. At least in this computer, the long is treated as an 8 byte. Okay, that's what it shows. So 8 byte is enough to store any address in, and it's in my computer. So it's perfectly valid to cast it and store it in a long. Okay, that's what I wanted to get across. All right, awesome. So these are fine. And then let's look at something, another topic, as in another concept. Right. Okay. Include the header file as usual. Define the main function. Okay. Define the integer I. Okay. So let's say that is 7. Define a long L, which is, let's say, I mean other integers. So 12, or double. 12. And that's D, which is equal to, let's say, um 7 4, so 4.9. Next, I need the pointer called ptr I, which is storing the address of the only integer we have here. Okay, let's go with that. A double pointer. Basically make a pointer for each of them. Okay, so ptrd stores the address of D. Do I make long? I guess it's not really required. Let's make for the void pointer because why not? Okay, and define that. That's it. Let's make a let's print it. Uh, we have defined some things, but let's print the value to be clear that what we're dealing with is the, as we expect. Okay, we have. How am I going to use nothing? I did it, and then so on, and yeah, this is fine. Right. Yeah, sorry about that. Okay, so let's print this and see. It is a main. Oh yeah, I think I got format this. Okay, this changed. Okay, got it. That's because yeah, it was because not format. That's fine. Okay. All right. So let's print this as in compile and run this. Okay. 7. That's simply it. We just declared some variables of different data types, integer, long, double, and pointers of some of those with a void pointer, and then define and then just call I to print and see what it is, right? So it makes things clear. We know what it is. Fine. Now let's start casting things. So I equal to D. Okay. So this is, and let me tell what it is. Is this allowed, not allowed? Can do this or not? Okay. This is implicit casting. It's allowed. Okay. So that's one. Same thing can be done to an explicit casting. Okay. So converting to an integer, D to be an integer, right? So this is this time explicit casting. Okay. Next, I equals to, let's say, the same thing. It's not like let's say, more like same thing. But this time it's what we'll do is a static cast. Okay. Reinterpret. We sort of reinterpret the pointer. Okay. Here not exactly as in downgrading or anything. It's the same number of bytes. Okay. We're just reinterpreting the data. In static cast, we actually change the data. Change it to integer. The same D. Oh, sorry. D has to be taken as parameter. So same D. So this is the C++ style explicit cast. Okay. All are equivalent basically. Here it happens implicitly. Here it's explicit. These two cases. I think that yeah. Here it happens explicitly, right? And here again explicit, but the difference is that is the C way, this is C++ way. Yeah, the word static is used to make sure that mm, you're converting from one user defined not user defined inbuilt data type to another, and sort of like you are if there is a chop off, it will happen. You're not reinterpreting the pointer. Here it's a variable that gets casted. Okay, so hence the word static, as in it's constantly translate that way. Yeah, yeah, we're simply forcing it. Yeah, essentially that's the thing. Yeah. We're not reinterpreting the pointer or anything here, or the variable as such. PTR is actually also a variable. Here, the pointer itself is a variable, right? We're not really reinterpreting the variable, as in here we used to reinterpret, right? To see the same pointer in a different, same value of the pointer, exact, to be fair, in a different light. Here, it's simply forcing it to be something else. That's all. That's where the static cast comes into picture. Okay. Now I can print the same thing. Okay. Let's just print this one out and then we move on. So the value is 7, yes, initially we printed, but then when we casted the to be stored in A, which was 4.5, the decimals get chopped off. So if now I has 4 now. Okay. Let's print D to confirm. What does it have? So D is still 4.5, which is good. Now we'll work with that. So we'll put D as I. Okay. This is the one form of implicit casting like we saw before. Making D as double that. So if the number is too big to be stored in integer, it will try to store it at how much ever it can. So technically speaking, if your number is too big for 4 bytes, or as in 32 bits, then it will just try to do the best it can. Won't be able to store it. Yeah, it might. It might as well. It will store. It will store probably the first 32 bits, whatever the equivalent of it comes out to be the new number. It will probably just give you like show you that. Now again, because we want to store larger numbers, you have to use longer data types to store that number. Yes, it is dangerous. Yes, that's a source of lot of errors actually. Storing or not realizing you are storing a larger number into a smaller number. Yes. From performance perspective, integers are faster than using long integer in a way because less bits to work with. And a lot of people just stick with integers thinking that that's the most they'll probably need. But so happens that in some case, as in while running the program, in some function, in some line, just so happens that what you calculated is too large for an integer. And let's say you return it, and that return function is storing into another integer. It's a source of an error. Buggy code can lead to a lot of issues. Yeah. So it is essential. It's becomes quite important to um, handle your data types pretty neatly. Yeah, so that you don't run into issues like this. Right. Okay. So this is the C style explicit casting. And let's go with the C++ style static cast. Yes, question is if I'm making a code for a okay, okay, and there I have to store trillions of okay, and that can't even store in long. What will I use? Oh, so that's the thing. Unsigned long int is quite a large number actually. So an integer stores, I think, till like 2.4 billion or something, and a number which is larger than that can't be stored in an integer. One can make it unsigned int. There is a boundary, yes. So let's say you make it unsigned int, you gain. So the range was for an integer was previously minus 2.4 billion to 2.4 billion. So it doubles the range, sort of. So you get 0 to 4 point, I think, 8 billion or something. So that it's like around 4 gigabytes GB. That's why previously when in 32-bit architecture systems, the maximum RAM supported, the size of the RAM memory, right, supported was 4 gigabytes. That's actually the reason. Now, let's say you want to store a larger number than that. You can absolutely use 64-bit. So usually just having long qualified to an integer is more than enough to make it a 64-bit integer and then use that. For most applications, the kind of numbers that we usually encounter, 64-bit representation of numbers is more than enough. I can take a quick look how big it is, but it's usually enough. Let's see what Google says. It's like around 1.8 times 10 power 19. Okay, that's pretty good. Yeah, even at that level, we don't have we usually don't encounter numbers that big. Like 10.19 is too huge actually. So yeah, again depends on your what do you call it, use case. In some use cases, they people have ways to get around this. So instead of 64-bit, you can define numbers to be of 128 bits and so on. I'm not exactly sure how. I think there is a C++ or ISO C++ um, what do you call it? A standard defined for this to if one wants to custom define 128-bit numbers and so on. But I'm not familiar with them. You can definitely look it up, but it's like you can extend the idea to 128 bits and so on. So there is a rule, how much of it, so in the 32-bit representation, there's a rule which says how much will be the exponent, how much will be the mantissa, how much will be the sign bit, and so on. It's defined. Same for 64 bits. So it's like three divisions. One is for sign, another is for exponents, another is for mantissa, so on. Oh, sorry, that was for my bad. That was for double, as in floating point representation. Since we're talking of integers, it's more or less like signed or unsigned, and the rest of it is just ones and zeros, right? So for integers, it's pretty much straightforward. So 32-bit can be easily extended to 64 bits, which can be easily extended to 128 bits. For integers, computers use something called 2's complement representation. So I think 128-bit is also pretty much extendable from previous cases. So one can use that. Again, 64-bit itself is too large, right? That's like 10 power 19 order of 10 power 19. So it's like saying every integer from minus maybe minus 10 power 18 to plus 10 power 18, something like that. I can represent exactly. So that's pretty good and more or less pretty much covers a lot of cases. So yeah, for double, the same 64-bit goes like I think 10 power 308 or something like that. That's a huge number. Granted, not every number from 0 to 10 power 308 can be exactly represented because of the floating point representation rules. As in, I don't know if this can be done, but I'm just giving an example. Let's say 7.2 times 10 power 32, or maybe not this simple, maybe 72222 with a lot of digits, which covers like 32 digits, right? This is a decimal representation. This number, whichever I just cooked up, it may not be exactly representable in computers. So there will be a range which it will fall into, okay? And those numbers can be exactly represented. So any number which comes in between that range falls into one of those. Like this is sort of, you can think like a lower bound and upper bound. Wherever this number falls within those upper bound and lower bound, and those two numbers can be exactly represented. There's a rule how one decides how this representation will happen. So then the corresponding um, floating point representation comes in. This is essentially floating point representation of double and integer. So there's some precision problem with double. Yeah, exactly. That's exactly why precision. There's a precision problem with doubles. Yes, you can't represent every number exactly. Not just decimals, even integers in double. After a certain range, you can't represent even all integers exactly in double. Yeah. All right. To learn more, you can. No, not exactly. Quantum computers, they do, how do you put it? They do a lot of things in parallel, yes, because of the states they have. But representing numbers also, how do I put it? They'll also sort of run into the same issues because you have enough qubits, right? So it's 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 actually a little different. It's not the same way how we think of numbers in uh, classical sense that it just probably will be bigger and better in quantum computers. It's actually not the same. It's a different paradigm, yes, but yeah. All right, let's move back to this one, and here I'll make it double if the parameter I and end it. So this will be a C++ style casting. All right. And let's say we run and print it. Oh, sorry, my bad. I need to print D also after this. Yeah, that's I think okay. All right, print score. That's because actually I think we can do this. So D is something we're storing I. I is 12. So let's comment that and see. So D originally was 4.5. Now we store I to it. I is 7. So great. And that we do it three different ways. Essentially, it does the same thing repeatedly, but the idea is still the same in all of this. Okay. Um, Taking another example, now we can look at some pointers as casting. Okay. All this at one. File stream, main function, return type, 0. Define integer I, let's 4, why not? Long as L as 10, then we have double T, which is 5.5 with it. This time an integer pointer, okay, ptri is address of I, then double pointer ptrd shows the address of D, and a word pointer. Did I have those here too? Oh, I did actually. I'm sorry. Um, this is not exactly my case. Sorry, my bad. So, void pointer, pointer B, and pointer. Now, what we'll do is pointer B, I can store ptri. Okay. Uh, can you tell me if this is allowed, not allowed? Will this throw an error? So be careful. Just think about it. So ptr B is a void pointer, and right hand side is also a pointer, right? So anything being casted to void pointer. Yeah, absolutely okay. That's fine. Not throw in anything. Similarly, I can store the ptrd also. It's absolutely okay. All right. Uh, I mean, we have seen this before, so I'm just repeating some to get the point across. The If I have ptr equals to v, I mean, what do you guys think will happen? Will this throw an error? Or what about this case? Yeah. So they will throw an error. We can't do that. Yeah. First ones will not throw an error. The second one will. Yeah. As we see, that throws an error because treating void as some other data type implicitly, yes, it cannot do that. That's not allowed. Okay. And then, yeah, this is fine. This is all right. Okay. So next is doing the same thing, but now we will use typecasting. You can convert, but not implicitly. That's all. Null is void, yes. But that's that's the point here. You can't do it implicitly. We can do it explicitly. That's what we're going to do it. So you convert it into integer pointer. Okay. This is the explicit C way. Void pointer. Okay. And that's it. This will be C style explicit casting. And the ptrd will be with double pointer, right? Which will be used on the same ptrd. Absolutely valid, absolutely okay. So this is again the C style explicit casting. Mention it's actually more specific type casting. I'm not right. Yeah. All right. That's good. format it, and then we try to run this. Absolutely okay. The C style is fine when we try to print, sorry, store one pointer to the other and just have explicit casting. Okay. Then what we'll do is make a pointer I. Yeah, exact the same way what we did when before. We did the same is C style explicit casting, but this time we'll have uh, the C++ style also. So pretty much the same thing. Static cast X. I think S can guess it. So it's the same PTI. So we did a pointer, okay, and takes PTI. Okay. So basically we copy the same thing, but call this C++. Okay. It was the same. Okay. So this is D instead of double. Sorry, integer, it will be double. Okay. All of these are perfectly valid. If you try to run, all right. Okay. All right. Yeah. So I'll end it with this learning. I mean, I've covered what I wanted to do today. In the meantime, if you have any questions, feel free to ask, or you can send them. Feel free to leave also. Okay, first question. Uh, you know, computers can't do anything by itself. So how does it know five is better than four and so on? Uh, okay. So think of it like an intelligent dumb, as in not call it dumb, but the idea there is that there is an algorithm. Okay. I mean, it follows the instructions. Computer doesn't think by itself. By that we mean is it doesn't know how to process five greater than four. It doesn't know what five is. It doesn't know what four is. It doesn't know what comparison is. But it knows a set of instructions. How, yeah, teach counting. Yeah, exactly. I mean, there are ways you can go about it. So what people did is first they represent. So let's take the example five greater than four. What people first figured out is how do we even store five? So we store five using some representation. So we came up with two ways for any 32-bit or 64-bit or whatever. Here the architecture really doesn't matter. Point is for integers, there is a 2's complement representation. For floating point numbers, there is the IEEE 754 floating point representation. Now they define a certain rules, and those rules is what people follow, as in they wrote the computers to even follow. Okay. So essentially what happens is five gets stored inside the memory, okay, using some representation of, let's say 32 bits. Four also gets stored. Now, to compare bits, there is an algorithm to follow. That algorithm is hardware coded, as in the hardware is made to compare bits. There's a whole process to it. It is probably beyond even my scope to explain, but the essential idea is that these ideas and algorithms of breaking down like every step of it and then doing them through the basic steps is how computers think. It's how we actually teach them to do anything. So a question like, let's say exactly the 5 greater than 4, represent the numbers 5 and 4, define something called a comparison operator, okay, like greater than, and then you just operate it. There's an algorithm, it will follow. It will store 5 in some space, it will store 4 in some space, and like a function, it will run that function which compares 5 greater than 4. That function is basically a greater than function. And then the return is, if it's true, as in 5 greater than 4 is true, then it will return true, or else it will return false. In our case, for the inputs 5 and 4, yes, it is true, so it will return false. It will return true. Yeah. How will to teach it counting? I mean that goes even beyond as in counting what. If you have objects in real world and you're trying to teach a computer to count, that's a whole paradigm because it has to be able to see the data and all. Again, that's the domain of vision. So that's a whole other thing we're getting into now. But simply representing numbers in with bits and digits, we have defined rules. Okay. If you are interested, you can read up on how we represent numbers, how we represent integers, how we represent real numbers. Even complex numbers also, there is an extension of that. It's essentially like storing two real numbers. So one can keep moving. So again, standard C++ has defined standard complex to work with complex numbers. So one need not worry. Yeah. I hope this sort of at least answer, I mean, clarifies, or maybe it's not complete, but so yeah. Any other questions? Very good question. So, uh, ideally, if you think about compilers, I mean, pretty much, well, they're written by very smart people, and they they do a lot of optimizations while the compilation itself. So if they see something, see an expression which has 5 greater than 4, and this can be evaluated at compilation time, depends on the compiler and the compilation flag, but let's assume it will do it for now. With let's say you turn on GCC's O3 flag or something, it'll most definitely do it. Because these expressions, if it can be evaluated at compilation time, actually we'll see that when we learn about templates also. So things which can be done at compilation time, it will probably do it so that it can optimize the code even better. So during the compilation, first it will read the code, it will input true at this place where we see 5 greater than 4, and then optimize the rest of the code accordingly. So the actual executable that you see will already have evaluated 5 greater than 4. Okay. And let's say this is a variable which we store it. So some bool equals to, let's say, flag equals to 5 greater than 4. So this flag itself will have true value. So sometimes it will not even make a variable to store true. It will just start substituting flag wherever we call flag as true. Okay, so can generate a lot of optimized code when you have constant it's const values, or you know some values to be known at compilation time. Then what happens is you have, of course, a very optimized code. Uh, yeah. So during runtime, code actually runs a lot faster in cases like this. Yeah. It depends what the code does, but yeah. So during, okay, to be fair, which one then knows is in the name of optimization, we'll use a lot of data. Actually, it's okay because A lot of times we care about the performance more, so that's fine. No, actually, to be fair, while compilation, it goes to the CPU also. So actually, CPU does a lot of this stuff. So it's not like I would say a compiler knows. It's more like the CPU definitely knows because end of the day, everything has to go through CPU. If you are running, I mean, if you're running only CPU based codes, so it's not even like losing data. It's about you have written a code to the extent you want it to. So compiler is just a set of instructions. Everything, all these instructions are executed by the CPU. Yeah, even compilation which happens for C++ code, it goes through CPU. It creates an executable and then stores it in some RAM or memory, storage even. So in our cases, it's stored in storage. Think of hard disk, SSDs or whatever. And when you try to run the program, that gets that executable gets copied to the RAM. Okay, whatever memory is for your system. Then it has a set of instructions which gets sent to the CPU. There's a talk between CPU cache uh, through PCI Express to the RAM. More or less, this is the roundabout way. We'll also see about file IO, how we write and read, write, store data. Then in those cases, you'll have like there's a connection to the storage that happens. In our cases, I should not forget, we have the terminal also. So there's a connection from CPU to the peripherals. So let's say you're putting an input, so keyboard peripheral, the terminal, so then a monitor output. So things like that. Yeah. Okay. I hope that also clears the doubt. So to be fair, optimization, we don't actually lose data. So let's say that flag variable that is compilation constant, but I'll still use the name flag to explicitly mean what I want to use at different places. I'll leave it up to the compiler to actually make those optimizations. But for readability purpose, I can still write those kind of code. And I actually don't lose any performance because I've left that compilation time substitution of the values and values to those variables to the compiler. So yeah, no, I would disagree that we lose data. Yeah, technically speaking, you don't actually need it. That's the thing about writing compilers. There's an intention by the programmer, which is the code, right? It has a flow, it has a structure, it has functions, it has variables. It's sort of a way we want our code to run or look like. So we just write it. How it actually performs, so usually best left to the compiler to decide because a lot of people have already figured that out. So yeah, as in one might think that there's some ways I've written the code, but compiler might decide uh, we'll execute this line first and then this line. It will give you the same answer, but the order of execution might be different. There'll be some other loads of optimizations built into compilers. Yeah. Actually having, yeah, okay. So questions assigning memory compiler or CPU. It's the OS actually, neither of them. So compiler and CPU do not assign memory. Compiler does know in statically, so you have arrays. So arrays which have predefined sizes. Then if the compiler knows those, so it will optimize the code as such. Yeah. Do you mean how a program works or runs? Is that what you're asking? What happens in the whole architecture system hardware when when a program runs? I think there are some tutorials or some lectures in the course itself where you can learn this. I'm not entirely sure, but what I'm speaking of is just some things which I've learned on along the way. Even I'm not sure where you can find these things. You can and actually just Google this stuff. So yeah, there should be resources to help you out. It's a interesting thought that going just beyond writing programs and running them, how everything um, fits together and so on and so forth. Yeah, exactly. How is access memory and execution all? Um, I'm pretty sure if you do a compiler course, they'll probably cover this maybe in first few classes. I'm not entirely sure if they do, but I assume they do. So maybe we can look at those. Again, these things are beyond the scope of this course, but I can just try to answer whatever I can, to the best I can. To answer the question that compile is a tool to control CPU, uh, that will be wrong. More like you write a code, it's translated into some instructions. Those instructions are sent to CPU. CPU then executes them and accordingly asks. So let's say that one instruction says print this data. So it will send a set of data to the peripheral, which is the monitor, connected to the terminal, right? So basically the display or wherever we see the terminal. So it does that and so on. It's basically a stream of instructions which CPU just keeps executing. That's its job. That's what it does. Um, Handling memory by a lot of processes. So there are things called threads and processes by in a computer. These are all handled by the operating system. In short, just OS. Your program is just one of many processes that's running in your computer simultaneously. Okay, concurrently, simultaneously, however you want to think about it. Now, all these programs uh, have limited resources. So there's only so many CPUs in your system. There's only so much RAM. So managing programs runtime, as in which one takes how much resource and what, that's all handled by the scheduler. Again, it's just you can think of it like an entity called OS. A part of it has a lot of uh, sub things like scheduler and all. They handle all this. Yeah. I'm not sure what C and G are, but yeah, probably. I mean, if you are interested in this direction, then yes, yes. Yeah. I see. Yeah. Yes. Maybe a basic course on computer architecture should cover these things. I've never formally done them, but I hope that they do cover this. So maybe you can look at those lectures. Maybe at NPTEL you'll have some lectures. You can probably take those. Yeah. Yeah, that's fine. I mean, it might seem a long way, but I feel the most fun you'll have is actually the learning time. So if it's a long way, you can think of it this way. The longer it takes you to learn, the longer fun you have. So yeah, As long as you're having fun learning, that's all that matters. Yeah. So in GPUs, uh, the way they work is little different. So there are no idea behind. I mean, there's nothing like a uh, storage like a class or anything. As in, there's just a pointer given. This data. It's going to access. Okay, I wouldn't say class. There are ways how GPU sees data structures. The essential idea is that GPUs take data pointers and then work with data. That's they're very bare bones. They don't have fancy things, okay, like what we see in CPUs. So there's a reason for that also. And essentially they try to process a lot of data and similar it's sort of like executing the same, yeah, parallel tasking, executing the same instruction multiple times on multiple data. Yeah. GPU itself is quite interesting. It's quite different than the architecture of CPU, how CPU and compiler for those. I mean, optimization wise, yes, but how our operating system will handle things on CPUs, it differs a bit more on GPUs. But yeah, thinking of algorithms, given algorithm which works pretty well in CPUs, might need to be changed or optimized a lot more if you're running on GPUs. So again, that's again research areas. So it's something what even I do in my research. So depends on the problem. A given problem can be parallelized. So essentially, what happens is we have a long set of lists and tasks. So let's say there is a code, like a huge code. So uh, a portion of it, which is most expensive, we try to parallelize that, and so on. So yeah, that's how we employ GPUs. GPUs cannot do all of the tasks that in a given code. It's sometimes impossible because they're not built to do those. So we let those tasks handled by CPUs and then transfer the data to GPUs to work with and then copy the results back. So essentially a workflow, what most GPU programming does. Okay. Yeah. Topic next week's let's see. I'll probably covering some operator overloading and templates. Yeah. I would say template is like one of my favorite in C++. Definitely quite useful to learn. So yeah. It does make template programming does make writing code much easier. Yeah. All right, exception handling and generics. Okay, I'll see if I can handle maybe cover those. Yeah. Awesome. Sure, sure. Awesome. Good night. Yeah. Happy coding.